Hi everyone, so I'm Kevin, and I'm here to introduce you to our project ATS, Adaptive Traffic System. So the motivation behind our project is that we all have our driver licenses, but one of the most frustrating things for me personally as a driver is waiting at a red light intersection when there's absolutely no traffic on the other lane. So we're just sitting there waiting, and we're wondering, why are we here waiting when we could be going? Well, we realize in cities like Philadelphia, this is because the traffic light systems are based off of fixed cycle times. So what this means is that the north-south lane and the west-to-east lane has a fixed cycle time of, let's say, 40 seconds. So whether or not there's vehicles actually moving or traffic on the other lane, you're still going to have to wait for the full 40 seconds. So intelligent transportation systems have tried to solve this problem by introducing induction loop sensors that are buried underneath the ground that detect the presence of a vehicle as they pass by, as well as pedestrian push buttons, which you've probably seen, and the pedestrian can push it to signify that there's a person waiting there. But there's a few problems with these systems. Number one, they're extremely costly. For a single intersection, it costs $150,000 just for the ITS system. Secondly, it requires heavy roadside construction. So you have to completely dig up the road, disrupt traffic, and it's really a hassle. And lastly, number three, there's no legal way to enforce the pedestrian to push the pedestrian push button. But more importantly, some of you guys might not actually know this, but if there's a 40-second time phase, you actually only have 15 seconds to push the pedestrian push button. So if you push it on the 16th second, you're doing absolutely nothing. So anywhere from the 16th to the 42nd, you're standing there pushing the button, but nothing's actually happening. So this is where our system comes in, the adaptive traffic system. We have three main goals. Number one, we want to reduce the cost to 1/4 of the current ITS system. Number two, we want to completely eliminate the need for heavy roadside construction. We want just simple installation on any given intersection. And number three, we want to have passive detection so that there really is no more need for that pedestrian push button and everything is passively done. So the way this works is that we have 4 cameras, 4 ping sensors, and 4 routers that will detect the presence of a vehicle as well as a pedestrian. And that's denoted by A, B, C in the graph, which we'll talk about later on. So now let me pass it over to Shreshth. We'll talk about how our system would be implemented in a real 4-way intersection.
Thank you, Kevin. So we put together a model to show you guys how our system would look like if we were to implement it in real life. So here we have traffic cameras, and these cameras detect the volume of traffic approaching the intersection. If we were to zoom out, we can see that we have 4 traffic cameras, and this is simply because you have a pair that monitor east and west, and the other pair would monitor north and south. Going forward, the other part of our ATS system is to detect pedestrians. So we first want to detect the presence of pedestrians, and we do that by using ultrasonic sensors. Once we know that at least one pedestrian is waiting on the crosswalk, we use Wi-Fi routers to determine the general number of pedestrians waiting. Again, if we zoom out, you guys can see that we have 4 Wi-Fi routers and ultrasonic sensors to determine the number of pedestrians at that intersection. Now I'll pass it on to Charles, who will tell us how these components play together.
Thank you, Shreshth. So now I'll walk you through an example in MATLAB to show you how our ATS works compared to a fixed cycle traffic light. So to begin, our system starts by giving fixed lights to both lanes here, so north, south, and east, west. And in this case, we use 40 seconds, starting with the green light for the north, south lane. However, while this is happening, our detection system is able to count 4 cars and 4 pedestrians that are trying to cross the east-west lane, but they can't because there's a red light. Now, after the 40 seconds, when the lights change from north-south to west-east, our detection technology is able to count 15 cars and 8 pedestrians that are trying to cross the north-south lane. But this number is far greater than the 4 cars and 4 pedestrians that we detected previously. So our system knows that there is a higher traffic concentrated on the north-south lane. So after the light changes, we leverage this fact to, instead of giving 40 seconds to the north-south lane, we give 60 and 20 seconds to the east-west lane. So because of this longer duration, we're able to see a higher flow of vehicles and pedestrians while keeping the Q constant at 5 and 4 in the east-west lane. So after simulating this in MATLAB of 10,000 trials, according to a Poisson process of a ratio of 5:1, we were able to see 18% reduction in the total number of vehicle queue, as well as obtaining 27% increase in both pedestrians and vehicles. Now I'll pass it over to Tom, who will explain more about pedestrian detection in greater detail.
Thank you, Charles. So as Shreshth pointed out earlier in our system, we have 4 routers detecting pedestrians. And in these router boxes, we want to mimic the current system of using push-button polls. However, the problem with push-button polls is that people do not actually push the button. Therefore, we propose a method using ultrasonic sensors in order to detect a pedestrian is there. These detect the pedestrian passively, which would be ideal for our system. How ultrasonic sensors work is that they send out ultrasonic waves, and then when it picks up an object, the returning wave would be determining the distance between the objects through time. So like say this sensor picks up the floor. The returning time would be much longer than say if Shreshth actually came into view, and the returning wave would be less. So the time would be much shorter. So yes, we would know the pedestrian is there. Now that we know a pedestrian is there, we want to know how many pedestrians are actually waiting at the corner. We do this through Wi-Fi detection. We leverage the fact that most people in the United States have a smartphone, and their smartphone most likely their Wi-Fi is turned off. So what happens is that your smartphone sends out what's called survey packets or ARP probe requests. And we collect these packets because they're publicly broadcast. And from these requests, we can determine what kind of phone you have. For example, this iPhone has a MAC address shown here. And we compare it and match it to our output in yellow. And from this output, we can determine that yes, this is actually an Apple iPhone. Now we can do this for all Wi-Fi devices within a certain radius. So in this case, we also detect laptops. However, we do not want to detect laptops. Therefore, we have to filter this output for non-mobile devices. And you can see here, Intel Corporation is not a mobile device. Therefore, we do not count it in the end. So what we do a final count, and we skip that after running through the entire list. And our final pedestrian count will be here, 9. So now I'll show you a live demo of our actual system running. So in this output here, this has been running for the past 5 minutes or so, and this is us detecting us within a 1 meter range on stage, as you see before. Now, I'm going to run and try to detect most people in the auditorium here within an 8 meter range. So as you see running on the white screen, we're actually collecting these requests as they run. And the MAC address, all we do is collect the MAC address. These are public broadcasts. So these are basically analogies to saying, what's your name? And oh, this is you. So I'm Thomas, and my name is Thomas, and I collect, say, yeah, hi. So it's not anything intrusive. It's just identifying what kind of device you have. Ooh. Oh, we have an issue. Anyway, moving on. I'll leave it off to Kevin to talk about vehicle detection. Yeah.
Sure, so I guess we'll run it at that bit, just minor fixes to that. But in terms of vehicle detection, what we do is we have input video stream that's coming into our system. So this is taken by the cameras that come in a few seconds before the camera switches lights. So what we do is now with this input stream, we put it into our system, so we apply Gaussian mixture model, which separates the foreground as well as the background. So as you see in the picture, you'll see that the black represents the background and the white represents the foreground image, which is the moving car. So based on the moving car, we predefine a region of interest, so that's marked by the yellow. Now, once we have a region of interest marked, we can look at the white, and we call these blobs. Once the blobs reach a certain size, we call that as a car. So as you can see on the top left, you'll see that 2 cars are marked, and that's how we're counting these cars. So now I'll run you through a quick, video demonstration of how our system works. So this is a video footage that I took with my own smartphone camera when I was at the Huntsman Bridge. As you can first notice in the video, there's a big truck, and right behind the big truck, you'll see at the last second there is a small car following right behind it. You can see, if you look really carefully, there's actually pedestrians that are jaywalking right here. So you know that they're obeying the rules of traffic. If you also look even more closely, it's actually raining, so there's this environmental factor coming into play, but it doesn't really affect our system. Lastly, on the right-hand side, you'll see there's a taxi that's crossing by on the other lane, but since we're predefining a region of interest, we don't want that to show. So now by taking this and compressing the video size, downscaling the resolution, we spit it into our algorithm. So here's our system. We can see that here's a big truck that's coming in, and right behind the big truck, you'll see there's that small little car being counted. At the top left-hand corner, you'll see that it's constantly being updated with the account, and that's how our system is detecting the vehicles. If you notice once more on the right-hand lane, a car will pass by, but it will not be detected because it's not in our predefined interest, region of interest that we're talking about. So I guess moving on, we were saying how pedestrians don't really push the pedestrian push buttons, but you don't really have to take our word for it. We went to the Mayor's Office of Transportation and Utilities, and they gave us really positive feedback, and one of the things they said was, one of the problems we have in the city is the failure of residents to actually push the pedestrian push button. Many cross against the signal, as you kind of saw in the video. Being able to detect our customers without requiring them to push the button would be valuable. So, this is really what our system is trying to address, is to have this passive detection, and that's really the goal of our project. So I guess some of the tasks that we have moving forward is really to incorporate better sensors into our system instead of the ultrasonic sensors. We want to expand our model to the grid setting so that you'll be able to actually, I guess, not only just have one intersection, but multiple intersections. And lastly, next week we have a meeting with the Pennsylvania Department of Transportation, so we're pretty proud to present the research to them next week. So that's it for our project. We're now looking for any questions.
Our township has 4 intersections at the entrance to Industrial Park Road. About 4 months ago, they actually just installed a camera system for adaptive traffic control system. Are you aware of some of the commercial systems that are out there already, and how is your system working?
Sure. So I guess I could take that question. For vehicles right now, they're currently mainly using only traffic cameras, like you mentioned. But the problem is the cameras are really expensive. So the ATS system as a whole is $150,000 for a single intersection. The cameras usually cost about $5,000 or a little bit more for just one camera. So if you have 4 cameras, it's $20,000 for the single intersection. But in terms of what we're really trying to address is not just the vehicle detection, it's the pedestrian detection. So that's really where a novel approach kind of comes in, because as the trend progresses, right now, 57% of the U.S. population has mobile smartphones. As that number continues to rise, one day it is going to be something that majority of all the people in the U.S. That's really our sentiment.
Speaking of the pedestrian detection, how can you tell which direction a pedestrian is actually trying to cross as opposed to the sign over there?
I can take that question. So, in any given situation, there's always a green or red line. So if the pedestrian actually wants to cross, they will have cross the red. So if the pedestrian is actually waiting in the corner, most likely waiting for the other direction. So therefore, by logical reasoning, it's usually just one direction either way.
Is the video on the page? For example, if there was a situation of police activity, they will access the video instead? It's just motion like
So are you saying would they have access to that video footage that's available? So that would really depend on the Pennsylvania Department of Transportation or the Mayor's Office, whether they would be.
What it's doable.
Is it doable to?
Yeah, I mean, if you were before, that's already for hospitals.
Oh, yeah, yeah. So since our system is basically just an algorithm that takes in video, like I took, just a normal image using my own personal smartphone camera. You apply that to, our system, any image stream can be adapted to that.
You save it.
Can you save it? Yes.
Yeah.
I mean, I know right now, most of the cities, I believe, they store about a month worth of data.
Mm-hmm.
So that's about how long they have just for, terabytes of data that you have. And once they do that, they, delete it and keep the next one.
Suppose I'm riding a bicycle, what happens?
So you're riding a bicycle, if you're parking near the corner, we will detect you, you have a smartphone on. But considering you also should be waiting for the light as well. Because if you're waiting at the red light and if you're waiting at the red light, your bicycle should have stopped. Otherwise you'd be jaywalking or in this case, just crossing a red light where you're not supposed to do it.
So I guess in terms of our vehicle detection, that's determined by what blob size that we set. So if the blob size is small enough, then we would be able to pick up the bicycle. But since we set it at a certain parameter that we detect only cars and large trucks, so we have a cap size for the blobs. We could choose to ignore it or we could include it depending on what we want to do.
Right, I could be just waiting there because it didn't pick up.
to show how that working. It's just it's limited to a 2-meter radius. So it's currently running right now, and you see the output 4, 5. So it's basically counting up to maybe the second row. Yeah. So,
Thanks a lot.